Okay, so let's begin. So today I would like to talk about two topics. One of them is method of conditional expectations, and then I want to start talking about martingales. And we will talk about it also next lecture. So method of conditional expectation is a way of yet another way of de-randomizing an algorithm. It's essentially, we already seen it. It's what I did the last lecture to some extent, although what I did last lecture is called the method of conditional probabilities. Here I'm going to do expectations. And I'm doing it because somebody asked me at the end of the last lecture about de-randomizing tree SAT. And I mumbled something, a bit clueless. But then I thought about it a bit and I realized that, in fact, it's a very nice example. So it's worth doing on its own. So the basic premise is that we have a function f of x1, x2. In our case, we're going to think about those variables as being binary variables. But in fact, they don't have to be binary variables. But in our case, let's think about them as binary variables, 0, 1 variables. And f is some function. The way to think about f is that f, if I give you a value of x1 to xn, f gives you some value of the quality of solution. For example, the concrete example, we have some Boolean form, k, let's say three sat formula, and f of x1 with n variables, of course. And f of x1 to xn returns you the number of clauses in f that are satisfied by a random assignment. Sorry, number of clauses satisfied by this assignment, not random. Right? So you give me an assignment for the n variables. I just go and count how many clauses are satisfied. And what we showed earlier in the course is that the expectation, to remind you, a tree SAT is a formula where every clause exactly has 3 literals. So we showed that such in expectation, E of f, which is going to be a shorthand for E of f of x1, x2 to xn, we showed that this was 7/8 of m. Right? And the proof of that was based on a very simple idea that if I have a clause, let's say x17 or x13 not, and x, I don't know, 7, right? We have a clause like that. Then we have 3 variables. Let me write k because k would be more convenient for us to be clear shortly. We have k variables. There are 2 to the k different assignments. And as such, there is only one assignment where all the literals evaluate to 0. So 1/2 to the k is the probability of a random assignment not satisfying the clause. As such, this was the probability clause with k variables to be satisfied. So this is equal to 1 minus 1/2k. Okay, so of course, this readily implied if we have m clauses in f, then this immediately implied that there was an assignment in expectation in expectation, the number of satisfied clauses in random assignment is 7/8 of it, right? Because k is 3, so 1 minus 1/8 is 7/8, and we have m clauses, so it's 7/8 of it. So that's a very nice randomized algorithm, right? But the question is, of course, how to de-randomize it. Okay. So the key idea, which is going to be the key for everything, is to observe that we can essentially compute the number of expected clauses to be satisfied, even if I give you a partial assignment. So formally, I'm going to call it expectation of f of v1 to vk. Okay. So you're giving me the value of the first k variables, right? So formally, this is what it is, the expected value of f, right? F, to remind you, is the expected, in our concrete cases, the expected number of clauses being satisfied, right? But in general, it can be any function of the random variables, x1, x2 to xn, conditioned on x1 equal v1, x2 equal v2, and so on, right? xk equal vk. Right? So this is a conditional expectation, right? And this is of course, the source of the name of this technique. Okay. So let's observe that we can compute this expectation, right? Why can we compute this expectation? Well, I can take the formula f and I can evaluate it on the first, I can evaluate it on this partial assignment. What do I mean by that? I just scan it. And every time I encounter a literal that depends on one of the first k variables, I replace this literal by the value according to the assigned value, right? So there is x, I don't know, some clause x7. So I would just replace this by the value of v7, right? And similarly, if it's, I don't know, x9 not, I would replace it by the value of v9, right? The v's are zeros and ones, right? So I'm essentially just scanning the formula and replacing appearances of literals by concrete values, zeros or ones. And then I can just scan the formula. And now I have a SAT formula, I have a 3-SAT formula where how can the clauses look like? Well, some of the clauses might have already concrete values, right? If I have a clause that have value 1, then it doesn't matter what it is, this clause is going to evaluate to 1. This partial assignment already satisfies the clause. So that's good. On the other hand, it might be that I have a 0, right? Something like that. Then if I have a 0 or something, I can just eliminate the 0, right? So then I'm going to get the clause that is shorter, right? With only 2. In this case, it's going to be a clause with only two literals, right? Okay. So I can definitely do that. I just get, in the end of this game, what do I get? I get a shorter formula. I get the number of clauses that the partial assignment already satisfied. And some of the clauses are now containing less than 3 variables, right? It might contain 1 or 2. Okay. But now I have this new formula, and I have the 3 variables, right? The 3 variables are now kx1 all the way to until xk plus 1 all the way to xn. And they can, again, I'm randomly assigning to evaluate this function, right? I want to evaluate this quantity, right? Our purpose is to evaluate this conditional expectation, right? So what do I have to do? I have to go over all possible values of those remaining variables, right? So xk plus 1 all the way to xn have values 0 and 1, right? But then I can do it, right? It's the same reason that I could previously figure out what was the number of expected clauses to be satisfied. I can do this on the reduced formula, right? Okay, so let's try maybe again. So we have this reduced formula, which is f of v1 to vk, okay? And now G has, as we said, and out of this process, we already get a number T. T would be the number of clauses already satisfied. Number of clauses already satisfied. Okay. And then we have the reduced formula. And now we just go over every clause, right? And we write down the probability that it's going to be satisfied by the random assignment of the remaining 3 variables, right? So if a clause has 1 variable, number of variables, right? If it has 1 variable, okay, so there are no clauses with 0 variables, right? Because clauses with 0 variable, we deleted, right? If they are satisfied, we added them to the count. If they are not satisfied, we just deleted them and forgot about them. Now, if there is 1 and the probability of being satisfied is half, if it's 2, it's 1 minus 1 over 2 to the 2. So this is 3/4. And if it's 3, it's of course our friend 7/8 from before, right? So for every clause, we explicitly write the probability that it's being satisfied. If we add up all those probabilities, I'm using indicator variable for every clause, whether it's satisfied or not. The sum of those indicator variables are going to be the number of satisfied variables, right? So Zi is 1 if and only if ith clause in the reduced formula G is satisfied. We know the important thing is that we can compute exactly Zi equal 1. We can compute this exactly by this is just 1 minus 1 over 2 to the number of literals in the clause, right? So the expected number of clauses satisfied in G, right? This probability is, again, this is the expectation here is over the value of xk plus 1 all the way to xn, right? This is just going to be the expected value of sum of the Zi, which is, again, the sum of the expectation of Zi, which is just the sum over I of the probability of Zi equal 1, right? So this is a quantity we can compute, right? Okay, so this is my assumption. My assumption is that I have this function f. I can compute the for a concrete value of f, I can compute f. And furthermore, if you give me a partial assignment, I can compute the expected value of f. Right? And assume that I can do it deterministically, like we did here, right? Here, the computation of this expected number of clauses being satisfied was deterministic. Okay, so what our task is? The task is to, so maybe I should say it explicitly. So task compute deterministically an assignment that satisfies at least 7/8 m clauses of f. So I would like to replace the randomized algorithm by a deterministic algorithm. Okay, so we're going to do the same thingy we did last time. I'm going to draw this decision tree, right? 0, 1. This is for x1. 0, 1, 0, 1. This is going to be for x2. And we continue in this fashion. I'm going to draw you x3. Okay, and we continue all the way to level n, where the last level is xn, the value of xn. Right? So now we can kind of think about expectation in a very clean way, right? How do we do it? An assignment is just, as before, a random path in this tree, arriving to a leaf. In the leaf, I'm going to write the value of f on this, let's call this path pi. I'm going to write f of pi. In this case, I mean just the number of clauses being satisfied when I pick the assignment encoded by f, right? And now the name of the game is that for every node in the tree, the value I'm going to write in the nodes, let it make it maybe green, right? The value I'm going to write in this node is going to be the average value written in its leaves. Right? So the way to think about it is that the number written in this root of the green tree is the expected number of satisfied clauses if you picked this partial assignment arriving to this node. Right? In particular, the root of the tree is going to be the expected number of clauses being satisfied, which we know in our case is going to be exactly 7/8 of m. Right? Now, the critical thing, of course, if we think about it this way, is that if we have a node in this tree, let's call this value alpha, it's going to have two children, alpha L and alpha, well, let's call it beta and gamma, right? The value of alpha is just going to be the average of beta and gamma. Why is this true? Well, so beta is the average number of clauses being satisfied by leaf in this subtree. Gamma is the number of the average number of clauses being satisfied in the right subtree, in the leaves. The number of leaves are equal. And now with equal probability, you either go left or right? So the two choices have equal weight. So as such, the average number of expected clauses satisfied in this bigger tree is exactly the average of the two children. Okay, are there any questions so far? Because this is kind of the critical property we need. So now what's going on? We have this tree. This tree is huge. It's exponential size, right? We cannot afford to compute it. Now, what do we want? We want to start from the roots, and we want to find a path. Finding a path is equivalent to finding an assignment of the variables. We would like to find a path to a leaf that has a number written bigger than 7/8 of m, right? Okay, so, and the important property we have is that for every node in this tree, a node corresponds to a partial assignment, and magically we can compute the number written in this node efficiently, right? This was all this argument about a partial assignment and how to compute the expected number of clauses being satisfied in this residual formula. So we can efficiently compute, in fact, not only efficiently, in O of m time, right? We just need to scan the formula essentially. So we can efficiently evaluate the number in every node in the tree if we want, and we can do it without computing the tree. So how do we do it? Well, the idea is that we start from the root and we look on its two children. The number written in the root, well, we know what it is, but let's just call our black box and compute it. It's the empty partial assignment. We get the value, and then we compute the value of the two children, right? Now, so what I called beta and gamma, okay? Since the value alpha in the root is the average of those two values, one of them must be bigger. So I'm going to go on the edge down to the one that have a bigger value, right? What does it mean that I went to the down the edge? It means that it fixed the value of the first variable. And I will continue in this way, right? It's now, this algorithm works in any level. I get into a node of level I look on the two children, I compute the value written in the two children in those nodes. Again, I compute the value using my black box. The value written in the current node is the average of those two values. So one of them must be bigger or equal. So we continue we go down to the one that have a bigger value. And we continue in this fashion, right? So what do we get? We get the path in the tree, which is monotone, right? All the values written along this path are larger equal than the value of their parent, right? So this path goes from the root all the way to the leaf. The value written on the leaf must be larger equal than the value written in the root. So we found a partial assignment that found a full assignment, very important, because I had a leaf. We found a full assignment that satisfies 7/8 m of the clauses. And the algorithm was deterministic, right? So maybe let's first speak about running time. So the running time is we have n nodes. And for every node, we needed to do two evaluations for left child and right child. What's the number written in their children? The number written in the children could be evaluated in O of m time. So this is just going to be O of n, which is polynomial, right? It's pretty efficient. So the running time is O of nm. We found an assignment that is at least 7/8 of m, and it's deterministic. Why it's deterministic? Well, if you think about it, deciding which child to go to is, of course, deterministic, right? We go to the bigger one. If they're equal, we just pick the first one, let's say. And the function that evaluated the value written at the node was deterministic, right? It just essentially, it's computed an expectation, a concrete number. It was not randomized. Right? It argued about probability, but it's a deterministic procedure. So we are done. Right? We found a deterministic algorithm that satisfies 7/8 of the clauses. So what do we have here? What we have, this is a very special case, right? We have a case here where we have some function that is essentially a scoring function that depends on some random variables that are independent. I would go into how the expectation was calculated shortly. So we had a function that had, in fact, I'm going to discuss it now. We had a function f that had random variable n, 1 to n, independent, and we were interested we had a randomized algorithm that essentially did a random assignment and argued that the expected value is good, right? And now what I needed something slightly stronger. I needed a property that if I give you some values, say the values of the first k variables, then, okay, so to emphasize, V1 to V0, those are, in our case, for 0, 1 concrete values. Those are 0, 1 concrete values. So I needed the ability that if I give you some partial values, I can compute the expectation, right? And now, once we have this, we essentially could do this assignment. We essentially did the natural thing, right? We started assigning the variables one by one in a way that maximized their expectation. And we ended up with we ended up with an assignment that its value was at least the expected value. And we got a deterministic algorithm. Now, okay, how do we did this expectation? So again, the basic idea was here. You gave me a partial assignment, V1 to Vk. I went over the formula and I evaluated it with V1 to Vk. So every time I had an appearance of one of those variables that I have their values, I wrote down I replaced the literal by its concrete value, right? This implies that some clauses became 1 because they had an OR with a 1 value. Then I just marked this clause as satisfied and added it to the count, saying this clause is satisfied. If it was 0, I deleted this 0 or something is the something, so I just deleted it. And then I got shorter clauses, right? And then the idea was that now we got this formula that have mixed lengths, but it's easy now for you give me a mixed length SAT formula. I can still, for every clause, write exactly what is the probability that it will be satisfied, right? Essentially 1 minus 1 over 2 to the power of the number of variables in the clause. The reason being, because if you have k variable, there are 2 to the k assignments, and there is only one bad assignment. So it's always 1 minus 1 over 2 to the 2k. So I can write for every clause exactly what's the probability that it's being satisfied. And now I use the fact that, so I defined zi as an indicator variable saying this clause is being satisfied. I can easily compute the probability of this clause being satisfied. And then the expectation we wanted, the expected number of clauses satisfied in G, in this partial formula, was essentially the sum of the ZIs, right? If you think it about this way, then all the clauses that evaluate to 1, their ZI is just always equal to 1. And if they are always not satisfied, it's just going to be 0 for such clauses, okay? And that exactly is this quantity. So we can compute this quantity deterministically, right? There is nothing randomized here. And yes, we absolutely will end up probably with better assignment than 7/8. Of course, by now we know that there are SAT, max SAT cannot be approximated to better than 7/8. And the proof generates those huge three-SAT formulas where there is no assignment essentially that satisfies more than 7/8 of the clauses. So that's it. But yes, we in practice would expect it to be better. Okay. And yeah. And if you think about this algorithm, it really is a greedy algorithm, right? You're just you're just maximizing your expectation. It's a standard algorithm in optimization. Okay, you can use it in other problems. For example, you can use it on the Turan theorem that I showed you last lecture. So you can always find an independent set of the size stated in the last lecture. You can compute it deterministically. I'm not going to show you how to do it. That would be a homework problem because I think it's very cute and it would be a good way to make sure that you understand these ideas. Okay, so again, this is kind of a general technique, right? It's a limited general technique because you have to have this very special problem. But for this kind of problems, you have this general technique, which is nice to de-randomize it. And if you think about it carefully, essentially that's what I did last lecture. Last lecture, the settings were more complicated because we had probabilities and the probabilities were complicated. So I upper bounded them. And then I argued that the upper bounds had this average behavior. And I applied the algorithm to the upper bound, right? And but the same argument applies. And of course, you can use it for minimization, right? So you can find an assignment that is above the average, or you alternatively can find an assignment that is below the average, using the same argument, except that you go to the child that is smaller among the two instead of the bigger one. So I would like to talk about martingales. Okay, so martingales, the name is very old. It goes back to horse races, and essentially it was invented. You know, people believed that they had schemes to somehow always win, to bet in a winning strategy. So martingale became this winning strategy, and then people started looking at it, and it somehow became something completely unrelated. And the way to think about martingale is that it's a sequence of random variables that depend on each other, but they depend on each other in a very specific way. And I should say in advance that a lot of the things I'm going to show you would look very familiar because I kind of used martingale earlier in the course without calling them martingales. So the way to think about martingale is that it's a memoryless process. Okay, so I will define it more formally shortly, but so thinking about having a sequence of random variables. For example, think about it as having the amount of money you have after xi is the amount of money after the ith round. The ith round in a betting game. Right? So you know, we saw several betting games, right? So think about for example, the betting game where x0 is 1, you start with $1, right? And then in every iteration, you're allowed to pick some fraction beta I of your money, fraction of xi minus 1, right? Right, so at the end of the I minus 1 iteration, you prepare for the next round of the game. You decide which fraction of your money to bet in the next round. And then with probability, right, xi is going to be either you lose or win the bet. So it's either 1 plus beta I xi, if xi minus 1, you won the bet. Right? Or alternatively, you lost the bet. Right? Okay. Now, such a sequence is a martingale. Right? If, well, martingale should be emphasized with purple and stuff. This is a martingale if the expected value of xi given x1, x2 to xi minus 1. Okay, this is, so let me be careful because I want to give you the right definition. Yes. Okay, so here's the way to think about, it's definitely true in our case, right? Because why it's true? Well, the expected value of our game, right? The expectation in the example, right? In the example, we had that the expectation of xi given xi minus 1, right? Since we had equal probability of losing and gaining the same amount of money, that was just xi minus 1, right? And now if you think about it, the value of xi doesn't care about all the earlier variables, right? Essentially, the way to think about martingale is that you don't care about the history. You just care about where you are now and where you are going. You don't care about the whole history. It's a memoryless process. Yeah, so it's a memoryless process, and then you have this behavior, right? So then it's a martingale, right? So always think about it as a betting game. Now, of course, notice that those variables in the example, those variable x1, x2, x3, all the way to xn, they are not independent. Right? They are not independent because, for example, if I tell you that xn is equal to 2 to the n, right? And you started with $1, this means that the player always bet all their money and always won. Well, unlikely, but it's possible, right? So it's definitely not independent, right? If you tell me the value of xn, I can figure out all the values of the variables, right? But there is some kind of limited independence, right? The basic idea here is that at every step of the game, you're making an independent decision, right? So your decisions accumulate, they determine your current state, but in every step, you're making a step which is independent of what is independent of your earlier decisions. Maybe that's the right way to say it. It's independent of your earlier decision. It's not independent of the state you're currently in, right? It's a bit bizarre. Okay, questions about this? Okay, so why martingales are interesting? So the reason why they are interesting is because they capture very strong. Okay, so the way to think about it is that martingales, they have this more limited independence, but they have this more limited independence, but they still behave very close to being independent. So what do I mean by that? If you think about the betting game example, right? The betting game example, we know exactly what the expected value is, right? So with the martingale, we always know that the expectation of xn, right? What is the expectation of xn? So it's the expectation of the expectation of xn given x1 to xn minus 1, right? Which is, of course, the expectation of xn minus 1. Here I'm using the martingale property. And now you can use this, you can just apply it repeatedly, right? You apply it repeatedly, right? You're going to end up with the expectation of x0. But x0 was a concrete value. It wasn't a random variable. This is where our game began, right? That was the seed money of the betting game, for example. So this is just x0. Right? So martingales have the property that we know what the expectation is. And the important thing is that, as we already know, in fact, from Chernoff inequality, for the betting game at least, we have concentration. Strong concentration. Okay. There is strong concentration, but of course the question is how do we quantify it, and also why is it interesting? The betting game was not very interesting because we could achieve the concentration using Chernoff inequality. So the reason why it's interesting here is because there are a lot of very interesting examples of martingales which are essentially counterintuitive, right? So let's see some example of martingales. So let me go through them. Let's see. Right. So we already did the betting, right? Showing that it's a martingale. So that would be the first example. So martingales, let's do maybe the most, one of the most surprising example that I know. So this is the own. Okay. So own is just a way for a container, right? So you have a container and it has some black balls and some red balls, okay? And the name of the game is that in every iteration, so this is, let's assume that this is the initial ball. You have, let's say, B0 and R0. B0 is the number of black balls and R is the number of red balls. And now you put your hand into the urn, you don't look, you mix the ball, and you randomly choose a ball. Right? You choose the ball and you take it out. And now the name of the game is that put back C copies of the ball you took. Okay. So let's, for example, think that in our case, we had 3 black balls. And let's assume that we picked a red ball. And let's take C to be equal to, just to keep things simple. right? So you extracted the red ball, so you need to put back 2 red balls, right? So we put back 2 balls, red balls, right? Okay, and now we repeat this game. Okay, we might pick now a black ball, right? So if you pick the black ball, we need to put back 2 black balls. So it would be like that, right? Okay, so we can play this game. On and on, the game continues, right? And of course, every time we play it, the number of balls increases, okay? And you can ask, what is the percentage is the ratio of black balls in the ith iteration? Okay, so let's call this number xi. Xi is just going to be the percentage of the black balls, right? So now we can analyze it, right? The claim is that this is a martingale, right? This percentage. So one needs to prove it, right? So how do we prove it? Of course, the answer is correctly. So we need to verify the martingale property. Okay. So I'm going to copy some stuff, and then we're going to explain what I'm copying. Then I'm going to explain it. So let's see. Xi minus 1, C minus 1 plus Xi minus 1 of Ni minus 1 divided by Ni. Okay, so first observe that Ni, the number of balls after the ith round, right? This number is well defined, right? Because Ni is just going to be N plus C minus 1 times I, right? We start with N balls initially, and then in every iteration, we take 1 out and we put C back. So it increases by C minus 1. Okay, so that's Ni. Let me continue copying. Xi minus 1, Ni minus 1 times Ni. Okay, what is this? So Xi minus 1, this is the percentage of the balls in the end of the ith minus 1 iteration that are black, right? So this is the probability that they pick the black balls when they started the next iteration, right? It's exactly the percentage of black balls in the OM. So it's Xi minus 1. If this happens, what happened to the number of black balls? Well, the number of black balls currently is this. Wait. The number of black balls is this. Why is this true? Well, this is, we have Ni minus 1 balls in the on, and Xi minus 1, a fraction of them are black. So this is the number of black balls. And since we picked a black ball, that's going to increase by C minus 1. So this is this. And the new ratio of black balls is going to be this divided by Ni, right? This would be the rate of black balls in the new OM. The other possibility is that we picked a red ball. So this is red ball. Right. There's the probability we pick the red ball. Probability red ball, right? And if we pick the red ball, the number of black balls remains the same, right? So this is going to be the number of black balls. It remains the same, and we divide it by the number of new balls, and this gives us the new ratio, okay? And now we just need to do the calculation, which is not especially interesting. So should I do it or not? Let me do it, because I think this is one of those things that seeing is believing. Okay, so both things have ni, so we can just write ni, right? And it's xi minus 1, c minus 1, plus xi minus 1 and I minus 1, plus 1 minus xi minus 1, right, times ni minus 1. Just a second. Yeah. Okay, so this is this. Okay, now if you think about it for a second, which hopefully, let's hope it's correct. Right. So oh yeah, I kind of, okay, this is squared, right? Let's see. Yes. Okay. So yeah, let me fix this. This is going to be squared. So as I said, the calculations are not too interesting, but since they magically come up to be the right thing, it's kind of interesting to see y plus xi minus 1 squared ni minus, sorry, plus xi minus 1 n minus 1 minus, right? This is from here, minus xi minus 1 squared ni minus 1. So things cancel out. Hallelujah. All right. This is divided by ni. So this is so this is ni. Sorry about this tedium. I usually try to avoid this, but I think in this case it's worth it, unfortunately. Right, which is just xi minus 1 times ni divided by c minus 1 plus ni minus 1. But that's, of course, what's written in the numerator is just ni. So this is xi minus 1 times ni divided by ni. So this is just xi minus 1. Okay, I'm sure you're happy about this calculation. What did I show and why did I show it? all I showed was that this expectation is equal to xi minus 1, right? So this is a martingale. Okay, which is kind of surprising. Okay, let's see if there are any questions about this. Yeah, I'm completely. It's quite possible that I made some stupid. Oh yeah, this is xi minus 1. Thank you. Okay, and I'm sure there are other typos. Hopefully the class notes do not have typos, but what I do, what I do during the lecture is less typos proof. Okay, so this is kind of interesting. And somewhat surprising, I guess. Now, the more typical, oops, that's not what I wanted to pass it. The more interesting examples of martingales are what they called exposure martingales. Exposure martingales. Okay. So the idea with exposure martingales is that you have some random structure, but I don't show it to you immediately, right? I kind of expose it to you one by one as we go forward, right? So right. So let's speak about the edge exposure martingale. Edge exposure. Right. So the basic idea that I give you a graph G, okay, and at every step, I'm going to tell you whether the ith edge is in the graph or not, right? So G graph over n vertices, okay? And in the ith step, tell you if the ith edge, is in G. Okay, so I'm exposing the graph. So what do I mean by that, right? So think about the vertices of the graph being numbered 1 to all the way to n, right? So I'm going to number all the edges, right? There are n choose 2 possible edges. Right? And now I can describe the graph as just this sequence of Boolean values, right? For the ith value would be whether the ith edge in the graph appears or not, right? Where I ordered the edges in some predetermined length. Okay, why is this interesting? It's because I can do things like, think about the function f, function of a graph. Okay, so you have some function of a graph, for example, chromatic number. Okay, so the chromatic number is how many colors do you need to color the graph, right? So now you can define a sequence of random variables. Xi, this is extremely confusing. So okay. 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 Okay, so far this doesn't make too much sense, right? So I'm giving you a graph. I want to look at the chromatic number, and I'm telling you the status of the first I edges, right? So I have to tell you about something about the other edges. Otherwise, how can you speak about the expected chromatic number? So the assumption is going to be, assume every edge in G is present with probability P. Okay, so here's what's going on. I pick a random graph. This is, by the way, this distribution is called GNP. This is a graph where there are n vertices and the probability of an edge is P, right? So I randomly pick a graph G from this set. It's a uniform distribution, right? Every edge you pick with probability P, take it or not take it, right? So you get a random graph. Now I want to know what's the chromatic number of G, okay? Now, of course, this is hard, very hard to compute. It's computationally hard, but it's well defined, right? The chromatic number of G is well defined, right? And initially, I know nothing, right? X0 just asks you for what is the chromatic number of G. Okay, it's some quantity, it's going to be some concrete number, some number, right? Okay, and now what is the ith variable again? The ith variable is going to be the expected chromatic number of G when I told you the first I edges. I told you whether they are present or not, right? Okay, by the way, you can think about this as being vertices, right? It doesn't really matter too much. So there is a vertex exposure martingale and there is an edge exposure martingale, right? And sometimes you use the one, sometimes use the other. Think for a time being on the edge exposure martingale. I'm telling you the edges one by one, whether they are in or not, right? So the way to think about it is that what we really care about is X and choose 2, right? This is the expected number of f of G, where I tell you all the edges, right? I tell you all the edges where they are in or not, right? So this is the chromatic number of G. Okay. Now, the strange thing, this is fact, which I'm not going to prove today. I'm going to discuss it next lecture because it requires non-trivial amount of work of really understanding what the hell is going on. But the important fact is that this sequence, this is a Martingale sequence. Okay, this is a Martingale sequence, right? And in fact, in this case, if you think about it a bit, M, right, the number of edges. Well, M is this n choose 2. If you think about it for a second, this martingale, the value cannot change too much, right? So xi and xi minus 1 is smaller than 1. Let me explain this because this is kind of the key to everything. I told you the first I minus edges, and I asked you what's the expected chromatic number. Then I told you one additional edge, and I asked you what's the chromatic number. Well, if I add one edge, the chromatic number can change by at most one, right? Essentially, all I can do is force you to take those two vertices connected by this edge and change the color of one of them. So the expectation is going to really change by at most one, right? So this property, which is kind of, as I said, the most important thing for us, this is bounded differences. Bounded difference. Okay. And this is very powerful. Why is it very powerful? Because now we can speak about this series of variables, right? So this is Azuma's inequality. In this case, by the way, we need something a bit stronger, but let me just state it. Azuma's inequality. So Azuma's inequality says the following. If x0, x1 to xn is a martingale, then, and we have the bounded differences property. Okay. Then we have a very strong property, right? So we have that the probability of x0. So what is x0? X0, to remind you, is some concrete value, right? It was essentially the expected chromatic number of the graph, right? It's some concrete value, right? It's the beginning of the game, it's some concrete value. And then we start the process and we do things, right? And we look on xn, right? And we ask, what's the probability that this difference is large? Okay, and that turns out to be exactly something that looks like Chernoff inequality. I think 2m. Let me verify I'm not lying. Well, okay, I lied. There is a version like what I wrote, but this is. So m is the number of steps of the game, right? So x and xm larger than lambda m. This is smaller than exp of minus lambda squared over 2. Okay, so this says that the last, if you think about the chromatic number, it says that well, okay, I guess I need to be very careful, right? No, I think in fact the way I wrote it is the right way. Yes, okay. So in fact, maybe, yeah, let's keep it like that. Let me be a bit imprecise because anyway, I'm running out of time. So essentially what it says is that the end of the process, right? The end of the process in our case was the chromatic number of the random graph we chose, right? X0 was the chromatic number, the expected chromatic number on a random graph, right? And then we chose a random graph, right? What this Azuma's inequality says is that this quantity concentrate, because it's a martingale, this quantity concentrate, it's very close to its expectation, which is kind of amazing, right? Why is it amazing? So the reason why it's so amazing is because essentially it enables us to state that function on random graph concentrate around their expected value, even if we don't have any way of computing this expected value, right? So you have define any function you want on a random graph, define the appropriate, look on the appropriate exposure martingale for it, prove that there are bounded differences. And then what you get is that in the end of the process, you get the concrete value of the function on the random graph you picked. This value is very close to the expected value. And this is true even if you don't know how to compute this quantity, which is kind of, looks like an impossible thing to have. Okay, so in the next lecture, I would prove Azuma's inequality. Well, I wouldn't prove it in detail because essentially we already proved it. At least one of the proofs I used for Chernoff inequality was essentially the proof of Azuma inequality. And then we will speak a bit more on martingales. And of course, I would explain why this very strange series of this expected value of the function, as you expose this random graph, I would explain why it's a martingale. And